you so much. Can everyone hear me all right? Excellent, excellent. Good morning, and thank you for coming to my talk. As Dave mentioned, my name is Josh Schairbaum, and I want to talk to you today a little bit about, it's kind of a case study of how a group of people inside Rackspace automated network device provisioning across 6 data centers in 4 continents. So as you said, I work for Rackspace. We're the service leader in cloud computing, 9 production data centers around the globe, and our business model is built on the ability to adjust to customer needs quickly and efficiently. And as part of news from yesterday, we've definitely had it with patent trolls, and we are taking the fight to them and supporting legislation that makes it difficult for them to file frivolous lawsuits. So really excited about that. So additionally, we're one of the founders of the Open Compute project, which is essentially open source for hardware designs, along with Facebook and some other companies. We want to make cheap and efficient, vanity-free hardware that everyone can throw in their data centers. Lastly, along with NASA, we open sourced cloud computing with OpenStack, which is a massively scalable cloud operating system. And we're trying to prevent vendor lock-in, and this should be a benefit for customers as well as cloud providers. However, many people will be surprised to know even the cloud runs on physical hardware. There are still situations where it makes sense to have physical devices sitting there. The biggest and best computing environments in the future will be a hybrid of physical and virtualized resources. So here's a kind of a sample. This is a pretty common configuration that we have with a lot of our customers. They have a dedicated hardware firewall, a dedicated load balancer that then connects and routes traffic to physical hardware, a private cloud, or back up the stack through the public cloud. The firewall is most likely some type of Cisco device. The load balancer is probably an F5, but also possibly a Cisco device. And this is really the required setup that we have in order for them to access the internet. So, like I said, it's pretty common. Some challenges with automating network device is that, you can't run Chef on a Cisco ASA 5520. I mean, there's no, it's not in Cisco's best interest to use automation tools on their stuff that they didn't write. So, a lot of these things we kind of have to stumble across and provide our own automation capabilities. And additionally, because of the amount of vendors and there's no common operating system, it's to interact with a variety of different OSs. It's kind of problematic. And so what my group does is we try to abstract this away into a single interface. And additionally, some of another reason why there's not a great project for net device automation is that there are really very few companies that need to automate 80,000 switches and aggers. So, there are software-based networks that are coming this way, but those again still run on physical devices. So if the people that champion the software defined networks say, well, it's virtualized turtles all the way down, like, well, we're driving the last turtle. So. And it's still an immature technology. And many capital-intensive businesses aren't just going to throw away these devices that they've already paid for. So physical stuff is going to be here for a while, and we are hopefully going to make that as pain-free to everyone that's a customer in the future. So for the purpose of this talk, when I use the term devices, I mean physical hardware of firewalls and load balancers. And additionally, when I use the term configs, I mean sets of files that configure access control lists, port interfaces, VLAN interfaces, and static routes in the file. So a quick run-through of provisioning through time for network devices inside Rackspace. So we've experienced extreme growth in 15 years, and the business model, though, is to provide top-notch service. And so automation oftentimes has not only been unable to keep up, but it's taken a back seat to making sure that we deliver things just in time for the customer. But as we begin to face the type of scale that we feel the open cloud is going to provide us, we've placed automation on the front burner, and it's got many of the highest priorities throughout the company. So originally, every firewall and load balancer was people kind of copy and pasted configs, handed them around, emailed them. Clearly this sucked. There's fraught with errors. Everyone kind of does it their own way, and it's lack of standardization, human error, et cetera. So the next iteration was essentially a web-based configuration generator where we would tie into a global set of variables. We had some liquid templates, and they would type in some things, and then it would kind of generate a basic config. But that was also a problem because in the end, you were still copying and pasting into a terminal on a device. Additionally, the configs would get stale, and automation that has to be reworked in technology is probably the worst thing that's ever been created. So the last iteration was the thing that I think everyone kind of had gotten fed up and said, we're going to solve this problem for good. And so we went to essentially a hands-free automated system to deploy and configure these devices. It spreads across a whole bunch of groups inside Rackspace, and it's fully automatable. And it provides a standard set of configs. It's hands-off. There's fewer errors, and it's a victory for the support staff because they now get the configuration ready to apply really customer-specific things and provide it like extra value to them. So we call this process kicking the rack, and essentially what happens is a DC ops person takes, when we get a shipment of, say, firewalls in, they take it and they put it on a pre-config station where they load the most basic configuration possible, and then it kind of goes and sits on inventory. The next step is someone will, it's ready to be provisioned, they'll take it out, they'll put it in a rack, they'll cable it, power it on, walk back to their computer and move the device in a global configuration system to a different status. So that starts off a whole chain of events. There's an orchestration engine that kind of picks it up from there and kind of drives this process. And there are other services involved that store environment IP data, that communicate with the physical devices, and that actually generate the configurations. So this whole entire process is written in a variety of languages from soup to nuts. We've got Perl, Scala, Ruby, Python, Erlang, and C#. My group specifically does the Ruby and Erlang bits. So, but there were some challenges that we had, some hurdles that we had to overcome. To begin with, I don't know if any of you are super familiar with NetSec technology or NetSec lingo, but it's pretty dense, and it's if you're not familiar with it, it kind of takes a while to get acclimated to it. And software discovery is software development is discovery, and you're never more ignorant about a project than when you begin it. So that's why it's good while we always plan as much as we can right before. So that was a joke. All right, so here's just an example of like some of the words that you end up saying all the time with NetSec stuff, and not all of them mean the same thing. But for example, if a couple of NetSec guys are talking back and forth, guys or girls, they'll say something about a static route. Well, I mean that actually could mean several different things. It could be the route statement. It could be a static route mapping. It could be a static NAT. I mean, there's just the unfortunate thing is that I don't know if it's by the inflection of their voice or whatever, they seem to be able to tell the difference when they're saying the same words to mean different things, but it's hard to pick up on. So this is definitely a hurdle that we had to work to overcome. So testing physical devices is super unforgiving. If we had a problem, we couldn't just shut down Vagrant and regenerate the VM. There's really no way to roll back. And so if we could have possibly cut our access to the device off by configuring an access control list incorrectly, in which case then a DC ops person would have had to hook the Cyclade card up to get us access, and we'd have to undo it, kind of by hand, and then test again. So the test cycle is several hours long. Additionally, I couldn't have a firewall or a load balancer or a switch or an agger connected to my desk because we really need to have it kind of replicated with kind of customer like a customer-like environment. So it definitely requires human intervention. And I mean the worst thing would be you end up breaking the device. So in that case, we have to open a ticket with a data center operations. They then have to go pull it out of the rack, uncable it, probably cussing you the entire time, and put it back on the pre-config station, re-base config it, put it back. I mean, they don't like to do it because normally what they're doing is they're putting customer gear in racks that we make money off of. So they don't like to do this. So there were some things that we did that really helped us through. And some of them were kind of make once decisions, so we kind of made them at the start of the process, and it worked really well for us. So the first of these was kind of adhering to the rule of separation. In Eric Raymond's The Art of Unix Programming, he knows there's some of the Unix implementers use this thing when designing their operating systems, and it's basically the idea of partitioning mechanisms from policies. And another way to say it is separating interfaces from engines. And so like I said, it's mostly brought up when discussing operating systems, but it's also really useful to apply to other areas of software. And like the great benefit of it is that it creates cohesion and not coupling. Okay, so a mechanism is essentially, it's an element in a system that knows how a thing is to be done to complete a task. And that thing could actually be a policy, and I'll get to policy in a second. But the principle of separation requires that the mechanism should never dictate constraints to the policy. So the mechanism's kind of wide open. I do this thing. I know how to do it. You just tell me when to do it, and I don't need to know why. So in our environment, we have a substantial service called Fire Engine that's written in Erlang and that speaks to aggers, switches, and firewalls and load balancers through a combination of SNMP, SSH, and yes, Telnet. Okay, so policy is the second piece of this segregation, and the policy is basically it knows what work needs to be done, and it's kind of a lens on the mechanism that reduces the possibilities based upon the business need. So this was super important for us because we ended up segregating our services both through organizationally but also through functionally. And so, for example, the group that I work on. Our piece in this, we have two services. One is Fire Engine, which is the mechanism which interacts specifically with the devices. All it does is it talks to these net devices. And then we have another one called FireKick, which basically handles the policies of this is how you generate a configuration, this is the rules, this is et cetera. So the other thing that was a great benefit to us is we actually had to focus on organizational change. When you have a highly motivated group like workforce that is really focused on, okay, this is how we do it. I don't have time to think about how to improve it because this is how we're doing it, and we're making good progress. You kind of have to make them stop and say, like, look, we can actually just remove this entire class of problems, not necessarily just this entire problem. So what we did, we worked on focus on standards, establishing them, and then also making sure that they were part of these standards. And then finally, being as inclusive as possible with all the various groups. And like I said, this was super beneficial to us because in the end, automating a process is just as much about organizational change as it is about technical change. We could write all the code in the world if we want, but if the data center operations guy doesn't change the status in the global configuration system, and we never know that this device exists, like it doesn't matter. So the other thing is that in part of this inclusiveness, everyone kind of had a piece to play and a part to play, and so we were kind of unsure how to divvy up the work and how to partition it. So what we did is we worked really hard to create this kind of swim lane document, and it acted as a living document that we used as we went through it to kind of help define how this process worked. And essentially, you can see at the top here, each swim lane here, the first one is discovery, where the blue boxes represent statuses, the gray boxes represent actions, green is decisions, and we never hit a red, right? Essentially it just goes down, keeps going down. And the great thing is that as we're going through, we're troubleshooting this, we're developing it, we are able to use a common lingo with everyone, to establish some ubiquitous language, and this was super useful for us. Finally, when actually worked on developing our app, we really tried to make the guts, the domain, its own app, kind of its own library, and then established ports and adapters. And this idea, I think most people in the Rails community will be familiar with it when they hear the term like Hexagonal Rails, which Matt Wynn has done some awesome presentations on. And ports and adapters, hexagonality is a term originally coined by Alistair Coburn. And it's really awesome, and you should all read up on it. And it actually deserves like way more discussion than what I'm giving it at the moment. So definitely that was a benefit. And basically what it means is, kind of let's just conceptually say that our base app would live in some folder, and then if we wanted to have a console for it, if we wanted to have have it connect through a socket, HTTP, anything else, we would write specific adapters for it, and then we would connect to that adapter through the console or whatever. And that's been super beneficial. I mean, I know there's very few apps that need to connect through the web and the socket and a console or whatever, but we also do it on the back end. So we have an adapter to the global configuration system. We have an adapter to the LDAP for authentication, et cetera. Okay, then the other thing was that because we're all kind of coordinating together, it was really important for us not to roadblock others, just as it was important for them not to roadblock us. And so what we did was we deployed a walking skeleton almost immediately. We pushed the most basic app to production that we could that essentially just mimicked a successful request and response. So we established some test data and said, if you send us this test data, we will send you this response. And it was actually static. And we deployed it almost immediately, like the first week, I believe, that we had this out there. So that way, other groups that were relying on to integrate with us could start to kind of test the happy path initially. And then as we continued on in our sprints, we would just swap out static bits for dynamic bits, and they could just keep testing. And it was really awesome. And I actually, again, another topic that I want to talk about more in the future. But the reason why we do this is because you never deploy as fast as you want to. And the reason why is because of Hofstadter's law, if anyone's familiar with that. So basically, Hofstadter's law, it always takes longer than you expect, even when you take into account Hofstadter's law. So that's just why, invariably, we're not good at estimation. Okay, so those were kind of the decisions that we made once. And then we had some daily decisions that allowed us to turn these habits into repeated behaviors. Again, and look, almost everything I say comes from growing object-oriented software, domain-driven design. These aren't things that we've come up with. These are things that we've reaffirmed with our experience. So naming consistency is another one. Ubiquitous language, however you want to say it. If you go back and you think about the swim lane document, the different swim lanes were discovery, deployment, network preparation. We made sure that those words appeared in the necessary places throughout the code base. So for example, in the module that kind of were the service objects for each of these high-level steps, you can just see that these names are forever. So here's an example of an actual swim lane. So I've omitted air handling, logging, construction, et cetera. And this is kind of like the top-level entry point to the process. But basically, this is just a simplified swim lane thing. Device discovery, that's a step directly off of the swim lane. And then obviously the notifying the orchestration framework. And then as we look at the top-level swim lane, you can see that we correlate the MAC address, which is device discovery, and then notify the orchestration of the outcome. So we've kind of reused the names as much as we can. So then the other thing that we decided that we needed to do consistently was to provide the most general API possible. Because sometimes you have flexible consumers who have made their own trade-offs that don't allow them to be as nimble or as agile as you are, and so if you be a little more general, it kind of allows you to kind of, I guess, make it easier on them. Would be what I would say. So for example, the orchestration engine that we used, in orchestration engines, by their very nature, their convention is configuration. So to have it kind of drive a process in your company, you have to kind of configure all the steps and kind of tie them all together, and then say, it does this first, and it's kind of the embodiment of the swim lane in a single domain. So, but it's not super flexible in terms of they don't have a lot of metadata necessarily at their disposal. So what we did was we, instead of making them kind of reconfigure this constantly, we made it so that every step along the way used the exact same configuration, so they could just copy and paste it all along. So, for example, here's what one of the things that they did is obviously they made HTTP requests based on events that got fired. So the one-discovery is a friendly name, which is a piece of metadata that they have within the context of an event. And so instead of making devices ID, kicks, discovery, or some sort of more expressive API, we made it as general as possible and had them pass in like what the step was that they wanted to run, which decreased their complexity. And additionally, after we kind of had them configured initially, they didn't need to be involved at all, because that system is pretty stable, and we can just keep firing events, and it just runs. So that was good for us. So the implementation of that is really simple. There's the controller. It's like I said, it's nothing. So then here's the actual kick process itself. And up top is kind of where we have the mapping to the friendly name, to the number, to the steps. And it uses like a class method facade, whatever. So for whatever reason, I hate instantiating objects and then calling one method on it and throwing it away. So I just wrap that in a class method. It's just, I don't know, pet peeve that I have, I guess. So each step that you discover, and we can chain multiple steps together, you can cycle through, and it performs it, and obviously it does multiple things. But so this way we could kind of split our own steps up into as many steps as we wanted without having to change the orchestration engine's configuration, which also mirrored the configuration that they use for servers. So the final thing that we did is we really focused on service objects. And if you heard Sandy's talk this morning, I will make sure to mention that it's lower. You can find these service objects in the lowercase, not the uppercase. So they're really without, hopefully, a lot of the baggage that a lot of like kind of enterprise software terms come from. But essentially, these were high level composed objects that handled entire stacks of functionality. So we would build kind of at the lowest layer, like this is a task, all little bits of policy that called mechanisms, and then we would kind of build them up until they got to the top point, which was the discovery step, or the discovery step. So some benefits of this are so increased surface area. So by kind of spreading this out, we don't have we don't have a problem of God objects anywhere, because it's all so spread out and it's all composed, and it allowed more people to work on. More mouths were at the trough, basically, because we weren't kind of stepping on each other's toes. Everyone can kind of reuse what other people are doing. So that was like pretty exciting. So here's an example of a class that does not use service objects. And essentially, this is the device discovery that was in the example I gave earlier. So what it does is it discovers the device on the switch through calling a fire engine mechanism. And then it grabs the MAC addresses from it. And then it grabs the first one. And then it updates the MAC with the device, et cetera. And it just... if we ever wanted to do like any bit of this, like you kind of have to. It's harder to troubleshoot because you have to set up all these variables. Like if you ever just wanted to run, each of these things. So here's an example that kind of uses service objects. So it's essentially, it doesn't look substantially different, except that I can now step through this much easier without having to know kind of what those things are returning. I don't need to know that it's an array that has these methods on it, or an array that has these objects in it, or et cetera. I can just kind of chain them all together. So that's the chief benefits are composability, easier troubleshooting, and much easier testing. So that is basically what allowed us to automate network device provisioning, and we took what took several days of time into something that takes like 15 minutes now. So thank you. That's it.